Today we're going to talk about local linearity or linearization and differentials. So one of the things we've talked about quite a few times so far this year is that the derivative is the slope of the tangent line of a function, but it also is a good representation of the slope of the function at any given point. In fact, it is the exact value of the slope of a function at any given value along that function. So what we're going to do right now is we're going to start with using our graphing calculator to graph this function x cubed minus 7x squared plus 5x plus 2. So I'm going to go into y equals, and I'm going to plug in that equation, x to the third minus 7x squared plus 5x plus 2. And we'll hit graph. And we can see a portion of this cubic function. And what we're going to do is we're going to zoom in at any point you choose, but I'm actually going to choose this point where we have that little local maximum there. It's not sure quite what the values are there, somewhere between 0 and 1 for the x value, and maybe about 3 or so there for the y value. So we're going to go ahead and zoom in. So hit zoom and choose option number 2. And we'll just scroll up there until we're pretty close to that local maximum. And I'll hit enter. And it looks as we'd expect it to look. And then what we're going to do is we're going to just zoom in again there, right around that same point. And you can actually just move your cursor. It's still set on zoom in, so you don't actually have to hit zoom in again. Just go a little closer. And it's looking a little flatter each time we zoom in. And we're going to see that eventually it's going to start to look, even at that maximum that we were at, just like a complete straight line. And the more we zoom in, the more like a line it's going to look. We call that local linearity. Anywhere where a function has a derivative that exists at any x value, if you zoom in far enough, it's going to begin to resemble a straight line. That's called local linearity. And so we're going to use that fact on small scales to approximate the value of a function that we may not know the value of by using a value really close to what we're interested in finding. And so let's take a look at how we're going to do this. So I just set this back to our original zoom before we move back to our problem here. So the first thing that we're going to do is we're going to write the equation of a tangent line to a function at any given a value. And so we've talked before, what do we need to write the equation of a tangent line or of any line is we need a point and a slope. Well, we're already given the point. And what would the slope be of a tangent line at A? Well, the slope of a tangent line is the derivative, so that'd be f prime evaluated at A. So that's what our slope is going to be. It's just the derivative of our function evaluated at A. So using point slope form, it'd be y minus the y value, which is f of A, equals our slope, which is f prime of A, times x minus the x value, which is just A. So that's just what we've got in point slope form. And if we were to look at just what y equaled, we could just add that f of A over to the other side of our equation, and we'd end up with this equation, which I've called capital L of x. We're going to call that the linearization function, right? And so we've used a tangent line at A to say that we can approximate f of x at some value close to A using this linearization function, which is just the equation of the tangent line at A. And we're going to call A the center of our approximation. That's what A is called. It's the value that's close to the x value that you're interested in, where we can easily evaluate our function and the derivative of our function, because we're going to need to be able to evaluate our function and the derivative of our function both at A. And we'll note that this formula is only going to work if our derivative exists at A. If we had a corner and a cusp or a vertical tangent line, or discontinuity at A, this function, this linearization function, is not. What we're saying here is that f of x is approximately equal to the linearization function L of x, which is our tangent line at A. This is our tangent line at x equals A. Okay. And this only really works well for values of x that are close to A. So let's see if we can make this work. Let's use linearization to approximate the square root of 50. Now, the square root of 50, our function is obviously just going to be the square root function. So we're going to say f of x is equal to radical x, square root of x, with a center of approximation, A, at the closest value to 50 that we know the square root of. And that'd be, pretty obviously, 49, because we know that the square root of 49 is 7. So our A value is going to be 49, and our x value is the value we're looking for, which is 50. And so we're just going to go ahead and say that our linearization function, L of x, is equal to f of A, so that's the square root of 49, plus f prime evaluated at A. F prime is 1 over 2 root x. And so if we're evaluating that at A, that's going to be 1 over 2 times the square root of 49. And then times our x value that we're interested in, 50, minus the A value that's given to us, or that we found, of 49. So we can see this is just f of A plus f prime of A times x minus A. It's just the formula that we had a minute ago, and we've just evaluated it with A equal to 49, x equal to 50, and using f of x as our square root of x function. So now we'll go in and evaluate this. This becomes 7 plus 1 over 2 times 7, so 114, times 1, which is just, well, it looks like that's 7 and 1/14. And 7 times 14 is like it's 98, plus 1 would be 99/14. So it's a really good approximation for the square root of 50. And so what we're going to do now is we're going to take a look on our calculator and see if that actually makes sense. And it should. So let's go into our calculator again here. And we'll exit out of our graph. We don't need that anymore. And our approximation was 99 over 14, which is 7.07142857.1. And if we were to evaluate the square root of 50, we would see that that's 7.071067.812, which is pretty darn close. It's, it's equivalent up to the 1,000th place. We're off by, around 4/10,000ths of the true value by using this approximation, which for most calculations is going to be plenty accurate enough. So let's see if we can do this again. We're going to now this time just try to approximate the square root of 26. So once again, our function is just going to be the square root of x. And we're going to use A equal to the closest value to 26 that we know the square root of, that'd be 25. And then x will be 26. And we can imagine that the closer A is to x, the better of an approximation we're going to get in the long run. So our linearization function here is just going to be, and I'll write out the full actual linearization function this time. It's going to be the square root of 25, that's radical a, or f of a, plus f prime, which is 1 over 2 square roots of x, so 1 over 2 root a in this case, times x minus a. And let's see if we can then evaluate this. Looks like we get 5 plus 1 over 10 times 1, or 5 and 1/10. You can write that as 5.1 if you want, or we can write that as just 51 over 10. And that's our approximation for the square root of 26, which seems kind of 5.1 doesn't seem like it's really all that great of an approximation for the square root of 26. It's kind of like, that's kind of the thing you might just make up if somebody said, oh, what's the square root of 26? You'd say, oh, I don't know. It's about 5.1. But if we look back on our graphing calculator and say, what is the square root of 26? Well, it's 5.099019514. So really, we're only off by about, a little less than 1/1000. So it's actually quite a good approximation of the square root of 26. All right, this time we're going to look for a approximation of the cube root of 128. So we're going to have a different function this time. F of x is going to be the cube root of x, or x to the 1/3. We'll need to know what f prime is, right, in order to evaluate this. So we'll just note that f prime of x here is 1/3 x to the negative 2/3. And we need a good value of a that matches up with x being 128. So it seems like the closest number to 128 that we know the square root of is 125. Sorry, the cube root of is 125. So a will be 125. And so we'll just use our linearization function. We'll say L of x. In this case, we're looking for L of 128. Right? And it might be better if we write this out as f of 128 is approximately equal to L of 128, which is equal to, well, it's equal to f of a. So that's the cube root of 125 plus the derivative of f of x evaluated at 125. So that's 1 over 3 times 125 to the 2/3 power times x minus a. And so now we can just go ahead and evaluate this. The cube root of 125, as we know, is 5 plus 1 over 3 times 125 to the 2/3 power. Well, 125 to the 2/3, we'll cube root the 125 first, giving us 5, and then square it, which is 25. So that'll be 5 plus 1 over 3 times 25, and then times our 128 minus 125, which is 3. We can cancel out those 3's, and we get 5 and 125. Guess I'll write it as a mixed number here, but really it might be nicer to look at that as 126 25ths, or we could call that 1/25 is 0.04. We could call that 5.04. And let's just quickly go in our calculator and see what the cube root of 128 actually is and how close it is to 5.04. So in the math window, we can find the cube root down here. The cube root of 128 is 5.0396. So 68. So it looks like we're off by, less than 4/10,000ths yet again. So that's a pretty good approximation, 5.04 of the cube root of 128. And let's look at one more here. We're going to try and find an approximation for the cosine of 1.75. So clearly our function f of x is just cosine of x. And our x value is obviously 1.75, but we need to get a value that's a number that's pretty close to 1.75. And so we kind of got to think about that for a little bit. Seems like a pretty good value for that might be maybe pi over 2. Probably about as close as we're going to get there for something that's pretty close to that. Pi being 3.14. We divide that by 2, or we're 1.55. So that's pretty close to 1.75. And our derivative of f prime of x, is just going to be the derivative of cosine negative sine x. So f of 1.75, or the cosine of 1.75, should be approximately equal to L of 1.75, which is just our function evaluated at a, so cosine of pi over 2, plus our derivative evaluated at pi over 2, so negative sine of pi over 2, times x minus a. And if we go ahead and evaluate this, the cosine of pi over 2 is just 0. And the sine of pi over 2 is 1. And if we have a negative in front of it, that's a negative 1. So we've got minus 1 times 1.75 minus pi over 2. Well, that would just be, if you distribute the negative 1 through, pi over 2 minus 1.75. Well, it doesn't quite help us to just have that. It might be nice to know what that approximately comes out to be, and we can compare it to the true value from our calculator of cosine of 1.75. So let's go ahead and look in our calculator again. We had pi over 2, and then we subtracted from that 1.75. That was our approximation. Negative 0.179203672. And if we actually tried to evaluate the cosine of 1.75, we get negative 0.1782. So we're off again by about 1/1000. A pretty good approximation. We can use these tangent lines to approximate the value of any function, not just like finding the square root of some number or the cube root of some number, but for any arbitrary function like x to the 5th plus 37x, we can approximate about how much the y value might change in one of these functions if we know about how much the x value is changing and where the x value starts. When we do this, it's still a linearization, but we kind of refer to it as differentials. And when we do differentials, we end up treating the dx and the dy as separate variables. So we'll treat the dx as an independent variable, and the dy as the dependent variable. And dx will just represent a small change in the x value, whereas dy will just represent a small change in the y value of our function. And we know this equation to be true. Dy dx is f prime of x. So if I've now decided I can treat dy and dx as their own variables, I could just multiply dx over to the right-hand side of this, dy equaling f prime of x times dx, where again, dy is just a small change in the y value that's resulting from a small change in the value of x. And this is only going to work or be accurate on very small intervals of x, because again, we're not actually using the function to approximate the change. We're using its derivative, f prime of x. So if I gave you the function y equals x to the 5th plus 37x and said, let's approximate how much y changes if our x value increases from 1 to 1.01, we would just rewrite this then as dy is equal to the derivative of x to the fifth plus 37x, which is 5x to the fourth plus 37 times dx. And then we need to know what to plug in for x and to plug in for dx. Well, x is just our starting value. X is 1, whereas dx is the amount of change in x. So if we're going from 1 to 1.01, dx is just going to be 0.01. It's going to be 1/100. So we'll plug those values in. We'll get dy, the change in y, is approximately equal to 5 times 1 to the fourth power plus 37 times 0.01. And so if we evaluate that out, we get 5 times 1 plus 37, which is 42, times 0.01, or 0.42. And so that's telling us that if x changes from 1 to 1.01, the y value of the function x to the fifth plus 37x is going to increase by about 42/100. So let's take a look at this one. We're going to look for the value of dy, the approximate change in y, given the function y equals sine 3x, when x starts at pi and decreases by about 0.02/100. So first off, we'll just need to say that dy is equal to the derivative of sine 3x, which using the chain rule comes out to be 3 cosine 3x, times dx. And now we'll just evaluate that when x is pi and dx is negative 0.02. So dy ought to be 3 times the cosine of 3 times x, so that'd be 3 pi, times negative 0.02. And the cosine of 3 pi, that's the same as the cosine of pi, effectively. And the cosine of pi is negative 1. So this is 3 times negative 1 times negative 0.02. And the negatives will cancel out, and 3 times 0.02 is 0.06. And so this is telling us that if the x value of sine 3x goes from pi to pi minus 0.02, our y value on that function is actually going to increase by about 6/100. We can also take an implicitly defined equation like x plus y equals xy and use differentials to approximate how much the y value might change. So in order to do this, we're still going to need to take a derivative. And it's going to kind of look like we did derivatives implicitly, except now anytime we're taking the derivative of an x term, we're going to call it dx. And anytime we take the derivative of a y term, we're going to call it dy. So we're going to end up with the derivative of x is dx, and the derivative or the differential of y is going to be dy. And on the other side, we'll have to use the product rule. It'll be x times the differential, the derivative of y, plus y times that derivative of x. And if we're looking for the value of dy, we'll just need to go in and solve for dy, just like we solved for dy dx when we did these implicitly. So dy minus x dy is going to equal y dx minus dx. And on the left-hand side, we could factor out the dy, leaving us with dy times 1 minus x. And on the right-hand side, if you want to, you don't have to, but if you want to, you can factor out the dx, leaving you with dx times y minus 1. And we'll end up with dy is equal to dx times y minus 1 over 1 minus x. And if we try to evaluate that, we can see that we're given a dx value of 0.05, and we're given an x value of 2, but we aren't given a y value. So we're going to have to go back into our original equation, x plus y equals xy, and find out what y is when x is 2. When x is 2, that becomes 2 plus y. I'll write that up here. If x is 2, we have 2 plus y equals 2y. And well, I think pretty straightforwardly, we can see that if we subtract y to the other side, we just get y is equal to 2. And so if y is 2, we now have all the things that we need to plug in to find out what dy is. So we evaluate this when x is 2 and y is 2, and dx is 0.05. We should end up with 0.05 times 2 minus 1 over 1 minus 2, which will give us a 1 over a negative 1 there. So it's just a negative 0.05. And that's telling us that on that particular equation, if the x value goes from 2 to 2.05, the y value will actually drop from 2 by 0.05 units approximately. We can also take this idea and apply it to, well, not really a real world situation, but almost a real world situation. We have a circle that has a radius of 10, and it's increasing from those 10 meters to 10.1 meters. So without actually calculating what the original area was and the new area was and finding that exact increase in the area, we could use a differential to approximate that value. So we know that the area of a circle is pi times its radius squared. And so the change in the circle's area would be dA. Then we take the derivative of pi r squared, giving us 2 pi r. And the differential would say we have to multiply that by the change in r. Well, we know that our original radius was 10, and our change in the radius, our dr, was 0.1. So all we'd have to do is plug that into our result here of dA to find that the change in the area is 2 pi times 10 times 0.1. And that would tell us that 10 times 0.1 is just 1. So the change in our area of our circle is approximately 2 pi. And since this is a change in area and we were in meters, we'll call it 2 pi meters squared. And that's about all we're going to talk about with differentials and linearizations. We're going to look at next time a little bit about how these tangent lines can help us solve some cool problems and allow us to find x-intercepts of functions that we may not be able to find the x-intercepts of any other way. But that's it for today.